In this video, we're going to explore the concept of collision theory and connect it to energy level diagrams. We're then going to proceed to take a look at factors that affect the rate of chemical reactions. Remember, the rate again is how fast a chemical reaction goes, and we typically measure that in moles per liter second. So we can explain the rate of reactions and why reactions occur using the concept of collision theory, which is basically the idea that for a reaction to happen, you need to have collision happen between particles, between two or more particles. And so if they collide with the right amount of energy and at the right orientation, then a reaction can occur. So what that basically means is that not all collisions are going to result in a reaction. In order for a reaction to actually occur, the collision must be what's called effective. It must be effective. Otherwise, what's going to happen is the particles might bump into each other, the reactants might bump into each other, and then just bounce off of each other, and that's it. And they haven't reacted. So, for a collision to really be considered effective, there are two criteria that must be met, two specific criteria that must be met. The first criterion, or the first aspect that needs to be met, is something called a favorable collision geometry. And that just means that the reactants need to bump into each other with the proper orientation. So remember that molecules are 3D things. And so because they're 3D things, they actually will interact with each other the way 3D objects might. So you might need to have the reactant molecules bump into each other at a certain angle, and only a certain angle will result in a collision that's considered effective. So, for example, here, the way that these reactants have bumped into each other just is not effective. It's not the correct angle. The proper functional groups aren't facing each other, for example, and so they'll just bounce off each other, and no reaction has happened. Here, same idea. Maybe we don't have the proper groups facing each other, the wrong angle, and they just bounce off each other. Here, same thing. The wrong orientation, so they just bounce off each other. And here it's the same thing. But here, they hit each other with the proper orientation, proper functional groups facing each other, and that is deemed effective. And so a reaction actually happens, and you get a rearrangement of the atoms or elements within the compounds to form new compounds that are there. So that's our first condition that has to be met. It's not the only one. Sometimes you can still have the favorable orientation, the proper orientation, and a reaction still not occur, and that's because you don't have enough energy there. Typically, reactions require what's called an activation energy. They need a little bit of a spark in order to happen. Activation energy is represented by EA as a subscript, little a as a subscript there. And what it is it's the minimum amount of energy required to initiate a reaction. So if the minimum amount of energy is present, then the favorable collision geometry will lead to a reaction. If the minimum amount of energy is not there, then it won't occur. So that energy has to be present. And we're going to take a look how we can get that energy. But the point is that if you don't have sufficient activation energy, and if you don't have favorable collision geometry, then your collisions will not be effective, and the particles will simply bump into each other and bounce off each other without actually reacting. So let's take a look at a bit more of the concept of activation energy. Over here we have a graph. This graph here is called a Maxwell-Boltzmann distribution curve. And what it shows you is the energy content increasing towards the right side, and then the fraction of collisions. And here we have on this dotted line an EA, the activation energy. Essentially, only particles that contain energy at the EA or beyond, so this area under the curve, only those particles will result in an effective collision. So only these here are effective collisions. And anything before that does not have enough EA, and as a result, all this stuff under here would be ineffective. So these are not effective collisions, and so they would just end up bumping off each other and not reacting. So again, for a reaction to happen, yes, you need the proper orientation, but you also need to have the proper EA, the activation energy, the minimum energy for that minimum spark for the reaction to actually occur. So anything in the shaded area here does have the proper EA. If it gets the proper orientation, then it will react. Anything to the left of the shaded area will not react since it does not have the sufficient activation energy. Now, Let's take a look at these concepts and study them in a graph. So you've already seen potential energy diagrams previously. What we're going to do is we're going to take a look at potential energy diagrams again with the activation energy concept there. So potential energy diagrams, just to recall, they track the change in potential energy during a reaction. Let's analyze this graph here. Here we have a reaction occurring where CO plus NO2 will react to form CO2 plus NO. So that is our forward reaction. This reaction could go backwards as well. The CO2 and the NO could react and form the reactants, CO and NO2. So you have the forward reaction, typically is represented as the one going left to right, and the reverse reaction is the one going right to left. So you can consider this as both the forward and the reverse on the same graph. So essentially what happens is the CO2 and the NO2, they're going to collide into each other. And if they collide with the proper orientation, they may react. Now, the other condition that has to be met is that they have to have the right amount of activation energy. So you can provide that in a few ways. One way you can provide it is maybe by providing some heat with a hot plate, for example, or a spark. But what's happening here is we're providing a little bit of energy to this system, and the energy of the system rises until we reach the point where the activation energy has been met. Once the activation energy has been met, then a proper orientation will result in a reaction. And so that's what you see here. Energy changes are happening until we get down to our products over here, CO2 and NO. The point at which the activation energy was met is called the transition state. The transition state. So it's essentially the highest energy reached, and that's where you have the sufficient activation energy. At that point, when an effective collision occurs with the proper orientation, the molecules will form what's called an activated complex. It's essentially like an intermediate between your reactants and your products. It's very unstable. It's your reactants and products connecting together, breaking bonds, and rearranging bonds. So it's that intermediate between the two. It's transitioning from reactant to product at that point. But this will really only form if you're at the transition state where you have enough activation energy for the reaction to proceed. Different reactions will have different activation energy requirements. Generally, though, those with high activation energy requirements will be more slow than those with lower activation energy requirements. So, for example, if you think about gasoline in a car, if you kind of just leave it sitting there, it's not gonna combust by itself. And the reason for that is at temperatures like you have in your car without starting it, there's not enough activation energy there. So while it would want to combust with oxygen, if there's no activation energy, then the reaction just won't occur. So you need to have that minimum energy reached, and then activation complexes could form, and then the reaction can continue happening. So what you see over here is the activation energy for the forward reaction. Okay, because we're going forward right now. We'll talk about reverse after. The difference in potential energy between the reactants and the products, that is considered to be your delta H. So here, as you can see, we have a delta H that is less than 0, that's negative. As you can see, the reactants released energy and the products are lower in energy now compared to the reactants. So this part here, where between your reactants and your products, is considered your delta H. That delta H does not include the activation energy. That activation energy is just a spark that's needed. We don't count it in our delta H calculations. So again, here's a delta H. It does not include the EA forward. As a reminder, if your delta H is negative, that means you have an exothermic reaction. If your delta H is positive, you have an endothermic reaction. So if you look carefully, if you were to run this reaction in reverse, so this is the forward one that we just did over here. If you were to run this reaction in reverse, let's make it a different color. Make it green here. Going from CO2 plus NO to CO plus NO2, you'll notice it's actually an endothermic reaction. So from the perspective of going in this direction over here, it's now endothermic because your CO and NO are lower in energy and your CO and NO2 are higher in energy. So if you take an exothermic reaction and make it go backwards, it becomes endothermic. And it's the same thing the other way around. If you take an endothermic reaction and make it go backwards, it's an exothermic reaction. So a couple things to notice. The delta H for the reverse reaction will essentially be the same thing as a forward, just with the sign changed. So if I was doing the reverse reaction, my delta H would be larger than 0, so endo as opposed to exo. Okay. But what is different is the EA of the reverse reaction. There is a higher activation energy barrier in this situation here when I'm going the other way around. So the EA for the reverse reaction, you'll notice, is from the products all the way up to the activation energy, to the transition state point. So this is the EA over here for the reverse reaction. And in fact, there is a relationship between the EA of the forward and the EA of the reverse. Your EA forward minus EA reverse is going to be equal to your delta H. So you could, if you have any two of these, you can solve for the other one by rearranging that equation. Okay, so your EA forward and your EA reverse, if you subtract the EA reverse from the EA forward, that gives you your delta H for that reaction. And so if you have any two of those, you can solve for the other one and then fill them in on your graph. So that was a potential energy diagram for a reaction. We saw it going in the forward direction, and we also saw it going in the reverse direction. We're going to do some practice problems where we identify whether the diagrams are endothermic or exothermic. We're also going to try to identify the EAs and the delta H's going in both forward and reverse directions. And we're going to see if you can identify if things are endothermic or exothermic, and then how that changes your delta H as you go forward there. So that was a potential energy diagram. In the next video, we'll do some practice problems to consolidate what we learned, and then you'll have opportunities to practice the concepts that we learned in the practice problems listed below.